With that, it's my pleasure to introduce Ben Church from Stanford, who will talk about Shioda's conjecture on unirationality. Bye.
Thank you very much for the invitation. It's a pleasure to speak here. So today I want to talk about a property of varieties, which is called being unirational. It's a very classical property. So I say that X is unirational. And here I'm always going to mean the geometric notion in this talk. So it's certainly over an algebraically non-closed field. It's certainly very interesting to ask about this question also. But when I mean unirational, I mean over the algebraic closure. So I say if there is a dominant rational map from Pn over here is this K bar to X. Dominant. So this is a very nice geometric property of a variety, and I'm going to try to convince you that in characteristic P, this behaves extremely wildly and very differently than it does in characteristic 0. So the main case I'm going to be considering is the case of surfaces. So for curves, we completely understand the answer. This is just about what your genus is and if it's 0 or not. But for surfaces, the question of which varieties is unirational was over the complex numbers completely answered in the 19th century. And so here's a theorem. It's probably due to Castelnuovo in this precise form. It says that if X over C is a smooth projective surface, I'll just say a surface from now on, then the following are equivalent. So we could say that X is unirational. Equivalently, it turns out X is rational, meaning it's you can take this map to be one-to-one generically. And there is a completely numerical condition that tells you when this is true. You just need that the first Betti number of X, so that's the dimension of H1, should be 0. And the second plurigenus of X, that's the dimension of the space of canonical squared forms. This should also be 0. So it turns out that these two numerical invariants completely tell you about when they're unirational over C. Now, so I want to talk about just a little bit, these numbers, right? These in general form obstructions to being unirational, even though in higher dimensions, it's certainly not an if and only if. But let me just tell you what's true in general. So the first thing you can see is that the fundamental group is an obstruction. So if X is unirational, it turns out that it's a tall fundamental group, say over K bar, is finite. And even more so, you actually can show that its order is co-prime to the characteristic of the field, which is a little bit extra work. And in characteristic 0, what that means, if the characteristic of K is 0, I actually mean that pi1 topological is actually trivial. So it's even better. So what this is telling me is that if my fundamental group is infinite, that's certainly an obstruction to being unirational. And that fits very nicely with this first Betti number being 0. Now, what's the role of this P2 invariant here? Well, that also fits into a more general story in higher dimensions of a sort of obstruction. So this is even easier. So we can say that if the characteristic of the field is 0, then moreover, there are just no tensor forms. So no tensor powers of the cotangent bundle has any section for all n. For all n at least bigger than 0. Okay, and maybe I'll just tell you what is the proof of this result right here. Well, it's very easy. So if I have a map from Pn dominating onto X, and I had a form here, I can consider the pullback of this form, which is well defined because this is defined away from codimension 2. And that would have to be 0 because there's no forms on projective space. But now we use characteristic 0 only to say that this map is separable at the generic point, right? This field extension is separable. Otherwise, you could have a map like Frobenius, which has 0 derivatives, and so it kills every form. And in fact, that really happens. So here's an example, which is due to Zariski, which says that you actually can get arbitrarily general type surfaces appearing in characteristic P that are actually unirational. So let's just consider an equation that looks like z to the p equals f of xy. Here P is the characteristic, and let's say just for simplicity that f has integer coefficients. So the claim is that this is unirational always, and it's unirational for a very silly reason. Well, maybe not a silly reason, maybe a very good reason, which is something about characteristic P, which is that if I do the substitution, x equals s to the p for some new variable s, and y equals t to the p, new variable t, and z equals f of st, then you can see that this certainly satisfies that equation, because what is f of xy? Well, characteristic P allows me to pull the pth power to the outside, and that is z to the p. So this, I've shown you, another way of thinking about it is that the function field of this variety lives inside of just k adjoin s and t, two indeterminates, which is the same thing as being unirational. Okay, so, but what's the point? The point is that f could be arbitrarily large degree. So this is going to, you can convince yourself that if you make f as complicated as you want, you can get the surface that this thing defines to have as many tensor forms as you want, lots and lots and lots of certainly pluricanonical forms, any kind of forms you want are going to show up. But you see that the parameterization I wrote down is a very inseparable, right? I'm taking pth roots of the variables. And so all the forms you could possibly write down, they have to be such that when you pull back along this map, they get annihilated by this inseparability. And this is one of the reasons that unirationality is so wild, because it's not controlled by the Kadeira dimension at all. It's not controlled by the number of types of forms on your variety. Okay, so this example is a little weird, but I actually don't find it that disturbing because I hooked into the equation the characteristic. Right? I think a much weirder example is that we can have equations where not just here, in this case, we just had one weird prime where things go wrong, and for probably all other primes, it's going to behave in a sort of normal way. But in fact, Shioda noticed that that is not the only thing that can happen. So here's, I think the way I'm going to state it, so this is a theorem of Shioda from 1974, but the way I'm going to state it is also due to joint work of Shioda and Katsura from 1977. And he showed that if you look at the Fermat surface, so that's x to the m, y to the m, z to the m, w to the m equals 0 inside of P3, and I'm going to think of it over the finite field Fp, then this is unirational. If and only if some arithmetic condition holds, which is that p to some power is minus 1 mod m, where m is the degree of that equation. So here for some power v. Right, so of course, this is a congruence condition on our primes, so there are infinitely many primes that satisfy this condition for every m. No matter how big you make m, there will be infinitely many primes that make this thing unirational. And in fact, those primes have positive density. And moreover, if you think about what is that density, it can be arbitrarily close to 1 as you vary m. So in fact, this is a really quite bizarre situation where you can have as big a set of primes as you want. It's not all of them, but it's a very large set that make this thing unirational. But as m goes to infinity, this surface is extremely general type. It's, it's the volume, say, of its canonical bundle goes to infinity, if you want a precise formulation. So I think this is a much more disturbing example. So, okay, so what is up with this strange congruence condition? Well, part of the way he proved this, and also what he noticed, is that this congruence condition, this is going to be related exactly to the eigenvalue of Frobenius acting on the Étale cohomology. So this is if and only if the Frobenius at P acting on H2 Étale of my variety there has eigenvalues which are of the form zeta, a root of unity, times P. Right, so this is the property that some power of Frobenius stabilizes the entire H2, at least when you divide out by this power of P, which is doing a Tate twist. So this is what the Tate conjecture predicts, is equivalent to saying that H2 is spanned by algebraic cycles. And in fact, he proved that. So this is the same as H2 Étale is spanned by the classes algebraic cycles. So actual homology classes coming from subvarieties. Of course, this can never happen for something with a non-trivial Hodge structure in characteristic 0. But the fact that it had some interesting Hodge structure in characteristic 0 is really lost at this prime from the perspective of algebraic cycles. Okay, so motivated by this and also a bunch of other examples that I won't have time to tell you about, he conjectured that actually this unirationality is completely explained by this cohomology property. So maybe I'll make a definition, which is that X, a surface over K, characteristic P, is Shioda supersingular if H2 Étale is spanned by algebraic cycles. And as I said, he conjectured, this is due to Shioda in a paper from 1977, that that if pi1 Étale of X is trivial, then X should be unirational if and only if it's supersingular, Shioda supersingular. So I want to make a remark, right? So we're setting pi1 equal to the trivial group because otherwise pi1 is an obstruction. Now, you might point out that in fact, I only said that being finite is the actually correct obstruction. So why don't you just put finite here? It turns out the conjecture is false in that case, and it's not for a very good reason that it's false. It's false because then you can pass to the algebraic, the universal cover, and the universal cover is still a variety, but it probably has a much larger Galois representation. And really, you should be asking about the properties of that Galois representation. And then if you make the conjecture with X replaced by its universal cover, Shioda did not know a counterexample. Although it is false because you can do things, these so-called Godot varieties where you quotient some Fermat like this by some group that kills all the interesting cohomology. But it's going to be unirational if and only if the Fermat was. So that's why pi1 trivial. Are there questions about the statement of a conjecture?
Sorry, is one of the implications meant to?
Oh, yes, that's a very good point. I think I was planning to say it before I said the conjecture, but so one direction is easy, and maybe I'll tell you how to prove it. So if you're unirational, you're supersingular. Let me tell you why. So is it difficult to see if I write on this board? Okay, so I guess
Maybe not at the top.
okay, so a remark is that I guess SSS, Shioda supersingular implies, is implied by unirational. So in the case of surfaces, it's very easy to see why this should be true. So let's take our rational map from P2. So we can resolve this by doing some blow up of P2 to get an actual morphism to X. And now the atomic homology of X is going to live inside the atomic homology of the blow up of P2 at some thing. But of course, the blow-up of P2's cohomology is algebraic cycles. It's all the exceptionals you added in plus the hyperplane. So now by tracing down, you get that this any subspace is also generated by algebraic cycles. So the images of the algebraic cycles here will be in algebraic cycles that span. Now, so it's the other direction that's very difficult. So what I want to tell you about today is a counterexample to this conjecture. So let's explain what it would mean to be a counterexample. I have to produce for you a surface with a bunch of properties. So the properties in particular that I got to tell you about are, so here's the theorem, 25, says that there exists a surface over some finite field. I will tell you what that finite field is at the end. I don't know all of them, which is kind of interesting. A surface with the following properties. So it better satisfy the hypotheses of Shioda's conjecture. So it should have a trivial fundamental group. And it also should have that its H2 is, supersingular. It should be spanned by algebraic cycles. Maybe actually, let me put this FP bar so that I don't have to put a bunch of extensions of my field there to be correct. But it's not unirational. And of course, number 3 is in some sense the most difficult thing, because one can view Shioda's conjecture, maybe this is a sort of not very charitable interpretation, but a non-charitable interpretation of this conjecture is set all of the obstructions we know equal to 0, then is the converse true? Is it actually supersingular? So to come up with a counterexample, the most interesting thing of this talk, from my perspective, is a new obstruction to unirationality. So I have to show you a new way to prove a certain surface is actually not parametrized by P2. So what I want to do now is tell you about sort of the story of how one can construct this parameterization, and we'll come back and I'll tell you what the surface is later. Are there any questions so far? This full example. So where I went to go searching for new obstructions was inspired by this work for complex manifolds where people are trying to prove certain properties called hyperbolicity. So in particular, in the algebraic setting, you could think of this as just asking the question, for which varieties can I prove there's only finite, or which surfaces can I prove there's only finitely many, say, rational or elliptic curves on? It's a conjecture, the Green-Griffiths-Lang conjecture, that if you have general type, if you're a general type surface, you should only have finitely many rational or elliptic curves. We don't know how to prove that in most cases, but there are some cases we know how to prove, and they all use the technique of studying certain algebraic differential equations. You try to cook up an algebraic differential equation that any curve with low genus would have to satisfy. And you try to prove that there aren't very many solutions to these differential equations. Now, this, of course, is very much works in characteristic 0. So we're going to have to talk a lot about how to make this kind of thing even possible in characteristic P. But so I guess the theorem, for example, that I want to talk about is a theorem of Bogomolov, which to my knowledge is basically the best partial result towards this Green-Griffiths-Lang conjecture for a general surface, not for specific classes like hypersurfaces, which says that if X is a surface which satisfies some condition, is a general, so it's general type, meaning it has lots of tensor form, it has lots of canonical forms. And it satisfies an inequality on its Chern numbers. So C1 squared bigger than C2. So here the canonical C1 is kind of very positive. So then the conclusion is true that X contains only finitely many rational or elliptic curves. And now the statement of this theorem is not going to be useful for us. Oh, sorry, this is over C. Very important. It's very much false over a positive characteristic, as this example shows you. Well, actually not that one, because there are examples. But I want to show you at least the extremely vague outline of how the proof goes. Because it's this proof that I think we're going to be able to extract some information even in positive characteristic from. So the idea of the proof is to use a symmetric differential form. So this is a section of the symmetric powers of the cotangent bundle. And so it turns out the first step in the proof, which is a huge amount of work, is to show that this inequality implies there always exists such a form. And then from there, we're going to analyze what happens to the rational curves. So I won't tell you anything about that. I'm just going to assume we have such a form and try to see what that has to do with curves. Oh, I should have. So the fundamental observation is that if I have a map from, say, P1, I'm just going to focus on rational curves, but elliptic curves, the same is basically true. If I have a map from a P1 into X, then automatically, right, the pullback of omega should be 0 because, well, there's no symmetric differentials on P1. Now, you could say the same with like a wedge power, but that doesn't tell you anything because wedge powers are always 0 on any curve. But this is an actual condition. This is telling me that the tangent directions of this curve live in the kind of the kernel of omega. Like if I plug in each factor of omega, the tangent direction, it says it's 0. So this is a first order differential equation that's nonlinear that this curve has to satisfy. So that's actually a real condition. And basically, Bogomolov shows, using some analytic arguments, that there are only finitely many algebraic solutions to this differential equation. And that's how he concludes.
That's true for any non-zero omega, or you have to pick omega carefully?
No, it really turns out it's true for any omega. I'm going to have to be very careful with how I choose my omegas. But it turns out Bogomolov does not have to be careful.
What's kind of the mechanism to show that?
Yeah, so the actual statement is I guess the easiest way of thinking of it is this theorem of Joannolu, which came later, but it makes it much easier, which says that if you have any foliation on an algebraic surface, then either the leaves of that foliation are all algebraic, in which case it's just coming from an algebraic map, or only finitely many are algebraic. And the technique is to show that, no, I think I'm not going to be able to say something both smart and correct about it. So maybe let's talk about it later. Okay, so I said something about foliations, and I want to connect this to a foliation, right? Because this is a little bit tricky because this equation is nonlinear, right? I have some powers, and I want to connect this to something a little bit easier to understand. What I guess foliations are still kind of nonlinear objects, but they're a little bit nicer to study. So one way of extracting information from the symmetric differential form is to use the following construction. So if you look at the projectivization of omega, so this is just pairs of a point on X and a tangent vector. That's all I mean by this notation, depending on your convention about duals. I just want to be clear. And if I have a map from any curve, I always get a lift right? So what is the lift? And I map a point of the curve to the point on X plus the tangent vector at that point. So I actually get a map to here. And there's a subvariety called Z of omega, which is just the set of points, comma, tangent vectors, so that when I plug into omega, I get 0. And that's a divisor. And so we can see that f of the pullback of omega is 0 if and only if the image of this curve lives inside of Z, basically by definition. But the point is that on here, by construction, there's this canonical sub of the cotangent bundle of X, right? The universal sub line bundle or quotient line bundle, whichever one you want to think about. And I can pull that back to Z. And the output of that is it turns out that this Z is foliated. It means it has a foliation F inside of its tangent bundle, some subsheaf, which is closed under the Lie bracket. That's actually automatic by it being one-dimensional. And the curves, the lifts of curves satisfying this property are leaves of this foliation. Right, so by a leaf, I just mean that the tangent direction to the curve sits inside of this F as you view it inside of the tangent bundle of Z. Okay, so then this is how I connect to that statement I said about foliations, that every foliation either has finitely many algebraic leaves over the complex numbers, or it has all of its leaves are algebraic. Maybe we can talk about later. So the point is that I want to now have some kind of analog of the control of the leaves in positive characteristic. Because of course, this construction, and this is almost completely tautological. This holds in any characteristic, works perfectly fine. What doesn't work is this analytic argument about the leaves of the foliations having certain algebraic properties. But we're going to be able to use some other tricks in positive characteristic to try to do something with this form. Okay.
And you have a map from E2.
Yes. So, okay. So here's something very funny, right? Which is that I am trying to answer the harder question right now, which is prove there's finitely many rational curves on X. I'm not going to succeed at doing that. It turns out all I'm going to succeed is in proving that it's not covered by rational curves, which is a stronger statement than unirationality. I said this because it's how the conjecture looked. But in fact, what I will prove is that it is not even covered by rational curves. In fact, it's not even covered by curves of genus 0 or 1. So I will actually prove this. But it's this is a very, very subtle point that I want to make now, which is that there is some advantage that you get by looking at one curve at a time instead of trying to analyze the entire unirational parametrization. So what do I mean by this? So I have this symmetric form, I'm assuming. And, right, so if I had a inseparable map, maybe this is a remark. If I have an inseparable map P2 to X, there's no reason, there's no reason G of this symmetric form might be 0. Is completely possible. But if I look at one of the rational curves, right, so I can take like a P1 in here and I get a map to X. This map still might be inseparable, but it factors through a bunch of Frobeniuses. Maybe I have to do some Frobeniuses to a P1 that's actually generically immersed in X. So this is like the derivative is not 0. And this is something special about curves, right? It's the fact that every inseparable map from a curve is just Frobenius. So when I take the image, I get something that it is a map from P1 and the derivatives are not 0. So the pullback of the form to omega being 0 is a real condition. Whereas in some sense, this wasn't really a real condition because the derivatives might just all be zero because of inseparability. So this is the point of studying one curve at a time. And I think it's very surprising that you're going to be able to answer the harder question when you try to ask the harder question. But this is the entirety of the advantage. The entirety of the advantage is we can still use derivatives to our advantage, whereas here we could not. There's just no way. Okay, so how am I going to use this? So the point is to somehow replace the description of the leaves that I said analytically. So I want a description of all of the leaves. Okay, I'll go here. So to do that, now we're going to work. Now from now on, it's really going to be positive characteristic. So here, characteristic of K is P. And in characteristic P, I have a new invariant of my foliation called the P curvature. Right. So this is the idea is that the tangent bundle is not just a Lie algebra under bracket, under Lie bracket in characteristic P. It's also a P Lie algebra because derivations can be sent to their pth power, which is still a derivation in positive characteristic. And we can ask if F is stable under that pth power operation. And its failure to be stable is a new type of curvature called the P curvature. So this is a map psi P, which if you want it to be linear, it goes from the Frobenius pullback of F is a foliation, to the tangent bundle of your foliated thingy mod F. So what does it do? It just takes a section of F thought of as a derivation, takes that to the pth power, that's a new derivation, and considers it mod F. It turns out this is linear when you do this. Mod F helps it be linear. And the point is this is zero if and only if F is stable under this pth power operation. And the reason it's useful from this perspective is that just like the curvature being zero, that's like being stable under Lie bracket, prevents you from being integrated, right? Like Frobenius's theorem in complex analysis or in smooth analysis tells you that you can locally integrate a foliation by a submanifold if and only if it's closed in a Lie bracket, which is the same as saying its curvature, in my perspective, is zero. And there's a similar thing, which is you can locally integrate the foliation algebraically if and only if the curvature is zero. So here's maybe a lemma, which says that if say C, if X F is a foliated surface, but it doesn't have to be a surface, foliated variety, and Z inside of X a leaf, so that just means that its tangent directions are everywhere inside of F, then it turns out that Z lives inside of the locus where the P curvature is zero. So that's what I mean by saying that it can only be integrated where the P curvature is zero. And in fact, there's some kind of converse to this. So the converse to this is that, or I don't know if it's really a converse, but it's another consequence we have. And moreover, if psi of P is just identically zero, so that's when this is a completely trivial condition, we still get a description of the leaves. And the description is via this new operation, which is called the quotient by the foliation. There's a map, the quotient by this foliation. And now you should not think of this, this is not like your characteristic zero brain where this reduces the dimension. This is an inseparable map of varieties of the same dimension. What you should think of it is do Frobenius, but only along the directions that F is pointing in. And it says if this is zero, then this map exists, and it has the property that Z being a leaf is the pullback of some Z prime that lives inside the quotient variety. So the way I like to think about this is the following. It says that it's not true that every leaf like the leaves of the foliation are uniquely determined by some initial data. And this is just because in characteristic P, there is no uniqueness for solutions to ODEs. X to the P is a solution to derivative equals 0. So you don't have any uniqueness properties of solutions to ODEs. So there's no hope that you could say all of the leaves are blah, like they're fibers of some mat. It's not going to happen. But what is going to happen is that they all differ by, they're all kind of parametrized by this other variety, by subvarieties of here, and they all differ by some kind of Pth power operation, right? You should think of them as all the leaves have to be P order tangent to each other.
Is there some simple model?
Yes, I'm about to write down the simple model. Thank you. So yes, exactly what this looks like is the following. So maybe I should credit, and this lemma is very easy once you understand the definitions of everything, but it was Ekadal who put all of these things together and made it a very nice theory of foliations in characteristic P. So the example to have in mind is the following. Let's suppose we have just a map from A1 to A2. So this is going to be given by T goes to two functions, f of T and g of T. And let me suppose that it's tangent to the foliation generated by del y. So this is a sub of the T of A2. What does this mean? Well, being tangent, right? So the partial T maps to f prime partial x plus g prime partial y. So being tangent is the same as saying that f prime of T is 0, which is the same as saying that f is actually secretly a function of T to the P. That's all this, really, that's the entire content. And so now what does being a function of T to the P mean? It means there's a new curve, a map from A1 to A2, which is the curve sending T to F tilde of T, G of T. And then I do this operation that looks like partial Frobenius. It sends X, Y to X to the P, Y. I just modify the first coordinate, and then my original curve is the pullback of this under this operation. All that is saying is I'm replacing T by T to the P, but only in one of the two coordinates. So that's why I call this a partial Frobenius. It does Frobenius half of the time. And you should think of this as locally exactly that, where if I had a local coordinate where my foliation is pointing along one direction, I'm just doing Frobenius in that direction. Okay, what's the point? The point, the entire takeaway.
So in your lemma, X mod F is still foliated and Z prime is a leaf, right?
I'm sorry, I didn't
In your
understand.
lemma, X mod F is still foliated and Z prime is a leaf.
No, this is any subvariety. So X mod F, it is true, it does have a foliation. Also, it's kind of like the opposite foliation, but forget about that. And I'm just saying where this is some subvariety. So it turns out any subvariety becomes foliated, right? It's because when you introduce T goes to T to the P, the derivative becomes 0. Great. So the point of this is to notice that if you think about what is like the degree of this map, it better be P times the degree of that map. It's bigger because you've input like a new variable, you've replaced one of the variables of T to the P. And that's kind of the entire takeaway. The entire takeaway is that we're going to be able to remember, where were we? Where were we? We had a curve on X. It was a leaf of a foliation. And I wanted to prove there are not very many of those. So what I'm doing is I'm saying if the P curvature is 0, I can quotient and find the curve as a new curve, as the pullback of a new curve on here. And the degree of that new curve is less by a factor of 1 over P. This is going to be the insight that's going to allow us to run an inductive argument, or like an argument by descent, where we produce curves of lower and lower degree forever. And that's going to be a contradiction. So let me now tell you how this obstruction really works. So this is at least the game you play. And then we're going to need one more idea to actually be able to run it in any case where we can compute anything. So the game the strategy is as follows. So I start with my original surface and I suppose that it has a symmetric form. So from this, I told you that the kind of Bogomolov construction on this board produces for you a new variety where I've replaced the form with a foliation. Okay, so and by construction, any rational curve on here, because it has to be killed by omega, kill omega, must lift to here. And now from here, we can say if psi p is 0, we can quotient. If psi p is not 0, we're already done, because there's only finitely many curves in the vanishing locus of psi p by that lemma. And so only finitely many curves can lift to here as leaves. But otherwise, you can quotient. And so now we get this x prime, which is z omega mod f. And all of the curves on here, all the rational curves, sorry, have to lift to there. And then they come from the pullbacks of here because they're leaves. Okay, so now this is where I wish upon a star. And I say, suppose there was an omega prime on this surface. There was a symmetric differential on here. Maybe on the resolution of singularities, this is probably really horrible, but whatever. Some symmetric differential here. Well, we have a rational curve, so it's going to lift to the next stage. We have like a z prime of omega prime, and that thing gets a foliation. And then assuming if its p curvature is not 0, we win, because all the curves that pass through this construction have to live in finitely many places. Otherwise, we keep going. We get this x double prime, which is the quotient of z prime by f prime. And then we hope, question mark, is there an omega double prime? And you keep running this. And the point is, if you can run this machine forever, like assuming all the p curvatures are 0, if one of the p curvatures is not 0, you win immediately. Otherwise, you run the machine forever, hopefully, and every rational curve, except for finitely many in some exceptional locus that I'm not going to talk about, but it's a finite number. Every other rational curve propagates through this insane diagram, and at each vertical step, it picks up a degree factor of p. So any curve that propagates infinitely far has to have infinitely large degree, which is a contradiction. So what you've actually determined is there's only finitely many curves of each degree, because what you've shown actually is that for each bounded degree, there's only finitely many steps it could go in, and it's going to have to land in one of the exceptional locuses after finitely many steps. So secretly, this would prove is finitely not covered by rational curves, which is the same as saying finitely many in each degree, finitely many of bounded degree. It turns out that there really are examples where this operation runs, but you have an infinite number of rational curves. They're just of they're of increasingly large degrees. Another thing that doesn't happen in characteristic 0. It only happens in characteristic p.
So is degree with respect to what that goes?
Yes, thank you. So that is a very good question. So I'm being kind of I'm lying a little bit. So one way you could do it is there is a way of choosing a sequence of ample divisors in such a way that it's going to work out. It's a little bit tricky, but in the examples I'm going to show you, there's a much easier definition of degree, which is my thing is going to have two natural projection maps to P1. And I want to say that the degree of the curve projected down to P1 or P2 is going to increase at each stage. So that's a much easier thing to keep track of. Okay, so the real difficulty is I wished upon a star here that there is such an omega prime. How are you ever going to do this an infinite number of times? So the idea is to say, well, if this process is self-similar, then you don't have to do anything. If you can cook up a variety so that when you do one of these steps, or maybe a finite number of these steps, you come back to the same variety, well, then you're in luck. Because then it's a finite amount of computation. You just need, for the finite number of steps you took, you just got to produce an omega on each of those. And then it repeats infinitely far. So how do I do that? So let's say x prime equals x. Then, of course, there will be an omega prime. I started with an omega on X. All right, so this is where I introduce the class of varieties that I'm going to talk about for the rest of the time, which are very simple. They have a very nice structure. So these are what I like to call product quotient surfaces for a pretty obvious reason, as you'll see in a second. So these are varieties that are they are the minimal resolution if you take the product of two curves, each having a G action, and you take the quotient. So here, I mean, this is a diagonal action, right? It just means that G acts on C1, G acts on C2, and I'm just acting on the coordinates together. So now, what's the point of looking at something like this? The point is that if I can cook up these foliations to literally be the foliations along the two obvious projection maps, one of the two obvious projection maps, then what is this quotient? Well, in that case, it's not just like some weird partial Frobenius. It's a more obvious sense of partial Frobenius. It's take this thing and do Frobenius in one of the coordinates. So want have to be along a projection, right? Because then X prime is just, say, I do like a Frobenius twist on the first curve, and I'll leave the other curve alone. And now there's some question about, is this the same surface as this? And not necessarily, but if you do a finite number of Frobeniuses, certainly they are the same, because this curve, okay, I didn't say it, but I want the curve to be defined over a finite field. Ci over FQ, right? So that when you do a finite number of Frobenius twists to your curve, you end up with the same curve. Okay, so how do you get this? So you get this if omega is what I call diagonal, which just means it looks locally like if you have Z1 is the coordinate on here, Z2 is the coordinate on here, it looks like some function of Z1, Z2 times dZ1 to some power times dZ2 to some other power. That's what I mean. So what I mean by that is you pull it back to C1 cross C2 and you look at where it lives in the decomposition of the cotangent bundle. You want to live in like one of the obvious direct summands and have no other terms. And luckily, you can actually kind of numerically prove criteria for when forms like that exist. So it's not, if you write down a random C1 and C2, it's maybe a little bit tricky to check if it has one of those forms. But it turns out that there's a completely numerical criterion for that ensures that one does exist. So why is it even difficult at all, right? It sounds like it's representation theory about the invariance of G. Well, it's a little bit tricky because this surface is singular. And you really need the form to extend to the resolution. Because otherwise, you're not going to learn anything about curves that hit the singularity a bunch of times. So you got to really do something with this resolution. And that's a little bit tricky, but it's not so bad. So here's like a proposition for my paper. So if X is one of those diagonal things, is product quotient, and I assume that some intersection number, I take the canonical bundle of this guy, I subtract off the exceptional divisor of the resolution. If that's positive, then there exists a diagonal form. Okay, so now we actually have an obstruction in unirationality that you can run. So for example, here's a theorem. Well, okay, maybe I'll take questions first. So this is just some numerical, completely numerical condition that is actually checkable. And it's not just checkable by a computer, it's not even that hard to analyze when it's true. So let me give you now a ton of surfaces that I can prove are not unirational of this product quotient type. So the reason I'm going to say what I'm going to say is because for the next 10 minutes, I'm going to talk a little bit more about number theory. I hope you forgive me for most of this talk being algebraic geometry. But I promised you a counterexample to Shioda's conjecture, which is something about the Galois representation of the curve. So I can't just choose some random curves. I really need to understand them extremely intimately. Like I need to understand their number theory. And so to do that, I'm going to look for Bellier curves. So I want to, these are the ones defined over a field, over a number field, but even better, I can look for the G Belyi curves. Right, what do I mean by G Belyi? I just mean its map, the curve to P1 is Galois with group G. So the reason these are very nice is because I can often figure out what field of definition the automorphisms are. Right, so such a curve is ramified at, say, 0, 1, infinity, what I'll call ABC. And what that means is that there's a map from this triangle group, ABC, which is, the thing generated by X, Y, Z, such that X to the A is trivial, Y to the B is trivial, Z to the C is trivial, and they satisfy X, Y, Z is 1. Right, and I'm saying that this delta ABC surjects onto G, giving it a certain presentation as a triangle, a quotient of a triangle group. Right, and then given actual elements of ABC, of X, Y, Z, which going to G to generate monodromy, that determines completely what C is. So I can actually tell you a ton of surfaces that are not unirational. I can say if C1 and C2 are G Belyi, and I have to make an assumption that with ABC distinct primes, I'll talk about that in a second. And G is the same group for C1 and C2. Then if I look at C, X is the product quotient of these guys in resolution. Then this thing is defined over some number field. And for every prime of good reduction, it turns out that, continue down here.
What are the final groups, G? What's G? What are the groups gonna be?
I'm gonna make us, yeah, sorry. I did not leave myself enough room here. So I'll have to make an assumption. So if the size of the group is big compared to ABC, then it turns out it's automatic that XP is not covered by rational curves. And if you care, this thing could be taken to be like e to the order log to the fourth ABC, log ABC. It's a completely log squared. It's a completely group theoretic question. I can talk to you about it later if you'd like. But so G has to be enormous compared to ABC, and ABC have to be distinct primes. But as long as that's true, as long as the group's huge, this thing is not going to be covered by rational curves. And it's actually very interesting because so when ABC are distinct primes, these groups are perfect. But if G is abelian, it turns out this is completely false. And why? Well, our friend, the Fermat surface, is a product quotient of Fermat curves. And Fermat curves are, in fact, Belyi curves, but they're like phi of n Belyi curves for a cyclic group. So this, and of course, n could be huge. So, it's not just about the order. The fact that this group is perfect is extremely important. And it turns out it tells you about kind of how many singularities there are, and it's very important to counting to make this work.
Where's the fact that G is perfect in the story?
Yeah, so the perfection is useful for showing that the centralizers of certain elements are small. And the centralizers control how many singularities there are of a certain type on the quotient. And if there's a million singularities, you're not going to be able to resolve, you're not going to be able to pull back the form and extend it over those singularities. You need few singularities. And that's about having small centralizers. And that's helped by being perfect. So what I really use is that there's this theorem of Shor that tells you about the sizes of certain subgroups if you understand the size of the center. Or rather, sorry, it tells you about the sizes of certain subgroups if you understand the size of the derived subgroup.
So in this construction, for which G are the XPs simply connected?
That's a great, very nice. Very good question. So it turns out that if C1 equals C2, and when I say that, I mean, of course, the same G-Belly map, right? It's not just the curves. Then I can't tell you when they're simply connected, but I can tell you that this product, that X is finite, like the topological, sorry, is finite always. So it's never an obstruction. So the pi, or basically never, only finitely many primes is an obstruction. So these are really new. And of course, you could also think about the Galois representations, and perhaps you can get an obstruction there. But for these enormous groups, I think we have no idea how to ask questions like, are there infinitely many primes of supersingular reduction? Probably not, but who knows? So this is definitely telling you something I don't think you could ever prove using supersingularity. Okay, I am a little bit under time, so I want to tell you now about the actual counterexample, because so far I haven't told you anything about Galois representations of those curves. So
The cohomology is algebraic.
I'm sorry, I didn't catch that.
And you did not say that the cohomology is algebraic.
Exactly, that's what I mean. So same thing, yeah. So so to get actual examples, I'm going to look at Hurwitz curves. Specific Hurwitz curves. So Hurwitz means that ABC is 2, 3, 7. And those numbers are very much not random. Those are the numbers such that the automorphism of the curve is maximized. It achieves the Hurwitz bound of 84 G minus 1. Right? That's because 1 minus the rate, the 1 over 2 minus 1 over 3 minus 1 over 7 is the smallest possible of that form. And okay, so why are these useful? Well, the idea is that if you make the automorphism group as big as possible for fixed genus, you're the most likely to constrain your Galois representation to be extremely simple, A, and B, you have the most different subgroups to try quotienting your product by. So you should think of this in some sense as, I tried all the Hurwitz curves, and this is the first one that worked. So it turns out that in genus 14 is the first example. I mean, there are not that many Hurwitz curves. This is not crazy, right? There's one in genus 3, the Klein quartic, that didn't work. There's one in genus 7, the Frichten-Macbeth curve. It also didn't work for, I think, more interesting reasons. And then the next one does work. So how do you get a hold of the arithmetic of this curve? Well, it turns out this is a Shimura curve. Actually, I shouldn't say this because there's exactly 3 of them. And that's explained by the theory of Shimura curves. Or these are Shimura curves. These are Shimura curves. They're Shimura curves for a totally real field, which is Q adjoined zeta 7 plus zeta 7 inverse. It's a totally real field. And a certain quaternion algebra, which is split at all finite places. Of course, that actually makes it unique. B is the unique quaternion algebra for this F, split at all finite places. So it's going to be ramified at 2 of the 3 infinite places and split at 1 of the infinite places. And how do you make a curve out of this? Well, the construction by Shimura tells you how to get an arithmetic subgroup. It says I choose O, a maximal order, and I consider the norm 1 elements inside that maximal order, inside of the norm 1 elements in B. And the point is that if I now choose I infinity is the split real place, this maps into SL2R, because at that split real place, B is just matrices, 2 by 2 matrices over R. So this is the unique split place. And this gives you a discrete subgroup. And so I can look at the upper half plane modulo this norm 1 elements. And the magic is that this turns out to be orbifold P1 with 2, 3, 7 central, what are they called? Orbifold points of orders 2, 3, 7. So what that means is that congruent subgroups of this thingy correspond, or just subgroups in general, but the congruent ones I'm going to look for give you the Hurwitz curves. And the important thing is that these Hurwitz curves, or I should say there's an arrow this way, they produce Hurwitz curves. Not every Hurwitz curve is of that form. And the important point is that you can compute the Galois representation of this thing in terms of the modular forms for these, these Shimura varieties. Okay, so now I am out of time. So I will tell you what the example is. So I said genus 14. How do you get genus 14? Well, you get genus 14 by taking the gamma of P13, which is the kernel of the norm 1 elements, mapping to SL2 of the OF.
It's full congruence level?
Yes, it's full congruous, mod P13. So here this P13 is one of the 3 primes inside the ring of integers of F over 13. So those 3 explain why there are 3 Hurwitz curves, because I could choose 3 different of these. So this is the full congruent subgroup for that level. And if I take X P13, which is just the Shimura curve generated by this thing, this is genus 14. And of course it has automorphism group equal to this thing, because that's its index. I mean, that's the thing how I constructed it. So the automorphism group is PSL because there's a ±2 ambiguity in SL2 in the SL2R action of K of P13, which in this case is just F13. So I have that thing. And now it turns out that the Jacobian of this X P13 is isogynous to 14 copies of some elliptic curve. And this elliptic curve is defined over the ray class field ramified at infinity and P13. And this field has a very important property, which is that it has a real place. The fact that it has a real place tells you that Elkies' theorem applies. So we only know that E has infinitely many primes of supersingular reduction because it has a real place. It's open whether or not things with an imaginary J invariant have infinitely many primes of supersingular reduction. Okay, so now I will claim for you, and this is the last thing I will say, that my board work is best thing. I will now just claim for you that if you can check, you can just check everything on a computer. I mean, in some sense, you can do this actually by hand, but I also have a script on my GitHub that does all the checks for you if you want to ever look at it for any good reason, which is that, so if I choose a copy of either D6, D7, or A4 inside of PSL to F13, so this is the centralizer of the maximal torus that's split. That's the one that's not split. And that's the exceptional A4 that always lives in these PSLs. So I choose any of these and I construct X0, sorry, not X0, X, I said 0 here, didn't I? No, good. I construct this surface, mod this G, which is one of those. This is, call this Y. This is simply connected. It's a computer calculation, you could say, or there's a way to do it by hand. KY minus the exceptional locus squared is positive. That means it has a symmetric form. And of course, we know that infinitely many primes of supersingular reduction by Elkies' theorem, because the Jacobian of the curves that it's constructed out of have infinitely many primes of supersingular reduction. And that provides infinitely many counterexamples to Shioda's conjecture. In fact, the numbers that you get out, if you just ask which primes are that supersingular for, you get these, you get 1091, 2337, and a bunch of other ones. But it's not CM, so this is actually a very sparse list. So a question for the audience is, can you construct an example where the Jacobian has CM? So there's a positive density set of counterexamples that I don't know how to do. Sorry for going a few minutes over.
Any questions for Ben?
So Fermat's favorite strategy was to
Infinite descent.
infinite descent.
Yes.
So I think you would approve.
I was, in fact, yeah, so I first thought of it as infinite descent, and I decided I would keep explaining it that way, even though, you know, induction is perhaps a easier way of talking about the same idea, but perhaps for that reason.
So how lucky are you here?
Yes, I think that's a great question. So I think I'm actually very lucky in the easiness of this, because this seems very complicated, but if you search for other examples, it's not easy to find them, right? So what you need is examples with reasonably large genus, basically because this is kind of hard to happen. You need the genus to be kind of big of the curves for it to be possible. And you need to have your Jacobian have a prime of supersingular reduction that I can compute. That's not usually the case, right? Maybe there are some primes of supersingular reduction, but they're probably really big. So I got very lucky that there is a curve of a reasonably large genus whose Jacobian is 14 copies of one elliptic curve, and that elliptic curve is defined over a field with a real place. That's very lucky, I think. Or at least it's lucky that I was able to find it quickly enough. I mean, the way I thought about this example was, I should try Hurwitz curves. They're the obvious thing to try. They have the most automorphisms. You have the most chance of being lucky. I tried genus 3. It was clearly not going to work. Tried genus 7. I thought it was going to work, but it didn't. And then the next one was genus 14, and everything worked out. So I think it is very lucky. But I think what we just
Maybe lower genus curves with automorphism groups that are not maximal, right?
Yeah, so I tried these like Arzela-McCollin curves. I can't remember. They're maximal curves of genus like 13 with maximum of automorphisms. So they didn't work. So I don't know. It's interesting. I think, yeah, right now I'm mostly interested in seeing if I can find some CM examples, but I really have nowhere to look because I don't know very many CM curves with large genus. So if anybody does
Yes,
it,
conjecturally, you've got Lang-Trotter type numbers of them. In other words, how many, if you take an elliptic curve,
yes.
there's how many supersingulars, the standard conjectures to how many there are. So, I mean, at least you know, you're not going to get a positive answer.
Of course. But what I mean is that if you had one CM curve, then you get a positive density set of primes.
Yeah, because
Yeah, but I agree that if you wanted to cover, so here I've only covered an extremely sparse set of characteristics. If you want to study cover every characteristic, well, you better have a really clever construction, or you better find some CM examples.
yeah, okay.
Did you always expect that Shioda's conjecture was false?
I think so. I think I uncharitably thought of it as set all the obstructions we know equal to 0, and then it's got to be true. And from that perspective, I wanted it to be false. But I would also say that every time I've talked to someone about this conjecture, they've said it's either obviously true or obviously false in approximately equal proportion. So I was in the false camp, but I'm not sure I had a good reason for it.
If we ask you to write down the equation.
Oh, yeah. Last time I gave this talk, I claimed that nobody, including me, knew how to write down the equation. If it turns out that is not the case, there is somebody wrote a paper in which they produced at least the defining ideal of the canonical embedding of a genus 14 Hurwitz curve. So in principle, it is possible. The equations are many pages long. And then you have to do the quotient by this non-abelian group, so even worse.
Did you try examples of genus bigger than 14?
Not a lot. So why did I stop at 14? Well, it turns out that's the largest that's computed in the LMFDB for higher genus families. So I tried a few things, like I tried the Hurwitz curve of genus 17, which I think also works, but its Jacobian is even harder for it. It's not just 14 copies. It's not like 17 copies of E. So you have to be more careful to find supersingular primes. But I think the numerics for the obstruction still works. It's just, I don't know about its Gauss representation as well. So I didn't try a lot of examples because the LMFDB was helpful, very helpful in finding examples.
Reason why the Jacobian is so nice here?
I would say it's a fact about the representation theory of PSL2 F13. So it's a very nice fact that this group has a representation of degree 14, that's an irreducible of dimension 14 that happens to show up in the Hurwitz character. And that explains everything, because once you have this giant irreducible representation.
The value representation? So it's the one that dimension P minus one.
There are 3 of degree 14, and I can't remember which is which, so I can't answer your question, but.
There's not, is there some, as we discussed.
Yeah.
A few months ago.
Yeah.
Is the problem, this group G?
Yes, so very funny coincidence. This group has order 1092. Interesting. I have no idea. I think it's completely coincidence. But maybe it's not. I mean, if you find out that it's not a coincidence, I think that'll be an even more interesting result. Yeah, I would say that it remains basically the only example I can find where everything works out. So I do think I'm quite lucky in this sense. I haven't tried that hard. One could do a really robust computer search to try everything. I haven't done that. I did do a computer search, and it was slow enough that it died before genus 14 and it couldn't find anything. And then I thought about it really hard and said I should try this example. So I think I did get very lucky.
Any other questions? No, let's thank Ben one more time.